Hello class. What I have in front of me here is a can of Coke, a fairly cold beaker, and one that's sitting in a warm water bath. Now I'm going to take the Coke here and I'm going to try to pour equal volumes in each. And I want you to predict what's going to happen. Do you think they're both going to fizz up the same height? Do you think one's going to fizz up less than the other? What do you think? What do you think? Make a prediction right now. Alright, so I'm going to take this nice toasty warm beaker here. This nice cold beaker. Our can of Coke. And let's pour in, let's try to do 100 in each. Okay, so we see a significant amount of fizzing in the warm. Now let's pour into the cold. We see also a significant amount of fizzing. That did not work nearly as well as I had hoped. However, what you'll notice, if we take a closer look, you can see that this one, the warm water beaker, do you see any additional fizzing happening? No, you don't, right? It's lost all carbonation. Whereas in the cold water, you see all those gas bubbles still that are forming? Well, it is still losing carbon dioxide to the environment. I was hoping to see a more stark difference between the two when I poured them in, but you can clearly see this one has not lost all of its carbon dioxide. Why is it that the cold one is now slowly fizzing where the warm one is now completely flat? So to understand that question, we need to understand what factors affect the solubility of a gas. First up is temperature. Temperature is inversely proportional to the solubility of a gas. So what does that mean? Right? We've talked about inversely proportional before. So as one goes up, what happens to the other factor? It goes down. So if we increase temperature, we decrease solubility. So if we look at that beaker of cola, the reason why the hot one was completely flat was that beaker was much warmer, that warmed up the solution, decreasing the solubility of carbon dioxide, and it all came out of solution quite rapidly. Right? It's much warmer than room temperature, so it all came out of solution very rapidly. Now with the cold one, we saw that, yes, there was still quite a bit of fizzing that occurred, but as that solution was further warming up, we saw more and more carbon dioxide being lost to the environment because there's still a fair amount dissolved in solution because it was cold, right? And there's greater solubility at a colder temperature. Now, I think I see the flaw already with my experimental design here. If I had started with a refrigerated can of Coke, the difference probably would have been much more stark between the two. Right? And you would have probably seen a bigger difference in the amount of bubbles produced. So, temperature impacts the solubility of a gas. Now, as the temperature increases, the kinetic energy of the particles increases, and this gives those particles more kinetic energy to break free of those solvent-solute interactions. And that is why that solubility changes with temperature. Right? We increase temperature, we increase the kinetic energy, and thus the ability of those particles to break free of their solvent-solute interactions and enter the gaseous phase. So that is the reason why temperature impacts solubility. As we decrease temperature, the opposite happens, right? It allows for those solute-solvent interactions to be more stable, harder to break, and thus solubility of that gas will increase. Here is a graph of two common gases that are dissolved in water, carbon dioxide and oxygen. One of the fears of climate change, global warming, is that as we increase global temperatures, there's actually these positive feedback loops that will further increase the temperature of our planet. And one of those is the ocean's ability to buffer the amount of carbon dioxide we put into the atmosphere, because a lot of that CO2 will dissolve in the ocean. But what happens when we increase the global temperature, the temperature of our oceans? Well, as we increase the temperature of our oceans, what happens to the solubility of CO2? It decreases, and thus the ocean can hold less dissolved carbon dioxide, thus more carbon dioxide goes into the atmosphere. So it's a positive feedback loop. Oxygen is an extremely important gas to the survival of complex life in waters. And as we increase temperature, we decrease the amount of dissolved oxygen. Usually, obviously, with climate change, this isn't a huge issue, but where this does become a huge issue is a lot of industries, a big concern now is thermal pollution, right? Part of the process in their manufacturing or their production of energy or whatever is they generate a lot of hot water, and this often gets dumped into streams or rivers. Well, if we dump a ton of very hot water into a stream, it's going to rapidly increase the temperature of the stream. And as a result, many of the aquatic species can suffocate because all of that dissolved oxygen, its solubility will decrease and it leaves solution, right? So thermal pollution is a big issue around manufacturing, around power plants, things like that. If they're dumping their warm wastewater into rivers and streams. What is the other factor that affects solubility? If we go back to our Coca-Cola example here for a second, what's going to happen to this can of Coke if I just leave it open and uncovered at room temperature? Even if I stuck it in the fridge and left it uncovered, what's going to happen? Is it going to go flat? Yeah, of course it's going to go flat, right? Of course it's going to go flat. So it's not just the temperature that's affecting its solubility. There's another factor involved here. What do you notice when you open a can of soda or you unscrew the top of like a 2-liter bottle? What's that sound you hear? What's that sound you hear? You hear a hissing sound, right? And if you try to squeeze the bottle before you open it, you'll feel it's very hard, and after you open it, it feels kind of like soft, right? You can compress the plastic. Why is that? Well, the other thing that has an impact on solubility is pressure. Now, pressure, the pressure and solubility of a gas are directly proportional. So if you increase pressure, you increase solubility. You decrease pressure, you decrease solubility. This is one of the reasons why if you're out in space and you rapidly depressurize your spacesuit, let's say a piece of space debris comes along and smashes your visor, well, you have a lot of dissolved gases in your blood, a lot of nitrogen, a lot of oxygen. What's going to happen when you decrease the pressure to 0? Well, that's going to decrease the solubility to pretty much 0. All of those gases are going to boil in your blood. You're going to swell up because of all those gases being produced. It's a really bad way to die. Now, increasing pressure increases the solubility of a gas in a liquid because when increasing the pressure, there are more collisions now with the surface of your liquid. More collisions, more interactions, and thus more gas will dissolve. So you get a greater solubility the more you increase the pressure. The lower the pressure, the lower your solubility. So what do you think Coca-Cola does when they bottle up their products? Do you think they use low temperature, high pressure, high temperature, low pressure? What do they do? Well, they want to dissolve as much CO2 gas as possible, so they will have high pressure, low temp, right? So at high pressure, increased solubility, low temperature, increased solubility. So this is bottled at high pressure. So when you open it, now you've decreased the pressure on the surface of your liquid. And after you decrease the pressure, well, guess what's going to happen? Solubility is now decreased, and thus the gas will start to come out of solution, and that's what you're seeing. You're seeing those CO2 bubbles come out of solution once you open your bottle of soda. You'll see all those little tiny bubbles that form in your glass, that form in your bottle. So, here's a little illustration so you can kind of visualize what I'm talking about. Here we have a piston, we have some gas. If we increase pressure, right, we decreased the volume, we're increasing the pressure. Those particles are now going to make more collisions with the surface of your liquid, and thus more will be able to dissolve. You are going to be doing an assignment on the bends. The bends is something that can happen if you are diving and you don't properly ascend. I'm going to let you look into all the details, but the bends is a nasty, nasty thing that can happen, and it all has to do with the solubility of gases within your blood. So, to get you started thinking about it, that is, when you are diving any body of water, if you go down 10 meters, that increases the pressure by 1 atmosphere. So if I went down 20 meters, that would be 2 atmospheres of pressure in addition to the 1 atmosphere I'm already feeling. If I go down 30 meters, that's 3 additional atmospheres of pressure. So you can see right away that as you go down, that pressure increases dramatically, right? If you ever watch those, old war movies where there's, someone trapped in a submarine, they're having some sort of submarine battle, and they have to dive deep down, and then the vessel starts creaking, you have nuts and bolts flying, and water starts to squirt in. Well, that's because the deeper you go, the more dramatically that pressure increases. So what is that going to do to the scuba diver? Think about solubility of gases. Okay, so that's all for today. Have a great day, everyone.